history of PN junction. PN junction A is rectified and allow current flow in one direction. In the forward bias, you will obtain a 0.7 volt. Under reverse bias, it will gradually reduce the drift current, resulting in a small reverse current, which breaks down voltage.
The process of fabricating a PN junction begins with an N-type or P-type doped semiconductor, into which the opposite type of impurity is introduced. To understand how this structure works and what physical process takes place in it, a didactic model is used. The model consists of a P semiconductor perfectly matched to an N semiconductor. The P semiconductor has a much higher hole concentration than the N semiconductor. Therefore, holes from the P region will diffuse into the N region and vice versa for the electrons from the N region. The diffusion of electrons and holes creates a region depleted of free charged particles, leaving behind the ionized impurities from which these charged particles come. Thus, two regions of positive and negative ionized impurities next to each other appear in the PN junction. This creates an electric field. The electric potential associated with this field acts as a barrier that prevents the displacement of the electrons and holes. Equilibrium is reached when the diffusion current equals drift current. The potential barrier is an obstacle for the diffusion current in the device. It is possible to reduce the height of this potential barrier by inducing external voltage. This increases the electric current. By applying an external voltage from a battery, the height of the potential barrier in the junction is modified. If a positive voltage drop is applied between the P and N regions, the barrier height is reduced. A reduced barrier cannot prevent electrons and holes from diffusing across the structure. An electric current appears in the junction due to the diffusion mechanism. Under these conditions, the PN junction is said to operate under forward bias. If the voltage is reversed and becomes greater in the N than the P region, the barrier height increases, preventing the electron and hole diffusion. The electric current is negligible. In conclusion, the PN junction can only conduct in a single direction, giving rise to a current which increases very rapidly when the potential barrier is significantly lowered.
PN junction quantitative electrostatic. At the equilibrium condition, we show the Venn diagram of PN junction, conduction and valence band gauge, electric field, and the charge density of a PN junction. For the formation of charge distribution for the barrier voltage, we can conclude that the barrier voltage equal to the equation below. For the depletion approximation of PN junction, we show the P side electric field and N side electric field. Find the profile of PN junction, finding the depletion width, integrate the rho S to find the electric field, and integrate electric field to obtain the voltage of PN junction.
An N-type doping adds atoms with one electron more than the substrate, say silicon. These dopants lead to the formation of additional quantum states in the energy gap. The electrons in these levels can be promoted to the vacant conduction band as the temperature rises, and the insulator can then conduct electricity. A p-type doping adds atoms with one electron less than the substrate, say silicon. These dopants lead to the formation of additional quantum states in the energy gap. The electrons in the bands can be promoted to these vacant levels, leaving holes in the valence band. These holes allow electrons to pass through the valence band. By forming a PN junction, it is possible to have electrical conductivity in one direction and not the other. This is called forward and reverse bias. An electric field must be applied to cause this to happen. A PN junction rectifies conductivity, which is turning AC current into DC current.
In a metal conductor, the positively charged particles are fixed in place, whereas the negatively charged particles, called electrons, are free to move around. A metal typically has an equal amount of positively and negatively charged particles, making the metal as a whole electrically neutral. If we apply a force trying to push extra electrons into this metal plate, we will not be successful, because particles with the same charge repel one another. If extra electrons accumulate inside the metal plate, they will repel each other and repel any of the new electrons trying to enter. Therefore, even if we apply force, the metal will remain electrically neutral. Now let us consider a new scenario where there is another metal plate close to the one shown. As electrons accumulate in the first metal plate, they will repel the electrons in the second metal plate. The positively charged particles left behind in the second plate will exert an attractive force on the negatively charged particles in the first metal plate. This makes it possible for the first plate to have more negative particles than positive particles. As we add electrons to the first metal plate, an equal number of electrons leave the second metal plate. After a certain number of extra electrons accumulate on the first plate, they will repel any new electrons trying to enter. The first metal plate has developed a net negative charge, and the second metal plate has developed an equal and opposite net positive charge. We can cause this equal and opposite charge on each plate to be larger by applying a larger external force. If we remove the external force we are applying, the extra electrons in the first metal plate will continue to repel one another. We have now returned to our original condition where the net charge on each plate is 0. The two metal plates are what we call a capacitor. Note, voltage is shown upside down in this video because the blue arrows will show electron flow. By briefly connecting the capacitor to a battery as shown, the two plates have developed equal and opposite charges. If we then connect the capacitor across the light bulb, all the extra electrons in the negatively charged plate will move to the positively charged plate through the light bulb.
This is reverse breakdown distribution of avalanche and tunneling of Zener diode. Example of P-type and N-type with wider gap of VR if higher electric field is applied to PN junction in reverse direction. A valence electron will make a transition. This process is called tunneling, in which electron penetrates through a energy band diagram. The energy band gap. The decreased energy band is equal to the width of VR in PN junction. After that, I will draw a smaller wide gap of PN junction with energy band diagram with tunneling effect. The first energy band diagram is avalanche multiplication and second is tunneling effect. Electron gains high kinetic energy from the electric field and collide with a lattice bond, creating an electron-hole pair (EHP). This newly created EHP will also acquire kinetic energy from the field and further creates more EHPs. This process continues, therefore it is called avalanche multiplication. This is example of graph doping concentration vs breakdown voltage of avalanche and tunneling effect.